briefly, because I'm not going into technical details here, but here and there I see that this is missing. So one question was, how do we make those images? I've shown you some pictures of very cold atomic clouds, BCs. So some people were asking, how do we do it? And it's the following. So how do we image our BC? How do we image it? Okay, it's simpler than it's as simple as taking a picture. We have the cold cloud in a trap. So I have my trap here, and the atoms are just in there. And my image consists, so I have, in the end it's all the same. But for early times, this was too small to do optical imaging. So you see diffraction, because it's a very small object. So we switch off the trap, let it fall. You have seen pictures where it's falling and expanding. So this falls, expands, and then what we do, we shine a resonant laser beam on it. What happens? Atoms, it's resonant to an internal transition of the atom, so they absorb the photons. And they emit the photons. But every photon that it's absorbed here is not here. So if I image with a lens on a camera, CCD camera, so it's just like the camera of your, it's the camera of your phone. I will have on this camera a shadow, an integrated shadow of the density distribution. So when I turn this camera to you, what you see is a shadow that is actually, you are seeing this dimension, and the integration of the density distribution in the other dimension. Okay, so it's a 2D image of a 3D object. Of course, if you have, two optical axes or some symmetry in your problem, you can reconstruct the 3D image. Okay, the 3D density distribution. This is how we image it. Literally counting how many photons are missing from the beam, from the imaging beam. Today, so in more modern experiments, we can bring microscope lenses, microscope objectives very close to the atomic cloud. So we can image with a higher resolution. So we can image the in-trap dynamics, and we can image we can image, just let me say to this that he should not stop. Okay, we can image single site, no optical wells in a lattice. Okay, this is how we image. Fine. Second, we were talking about yesterday about the bubble, the shell trap. And I told to you, okay, these atoms, they flow to the bottom of the shell, and we cannot switch off gravity, so that's why we go to space. But this is not entirely true. There are ways to switch off gravity, but that way don't work for the bubble trap. So I'll be quick on that, but how do I switch off gravity on Earth? I have to have atoms. So let's come like this. Every atom, or almost every atom, is a small magnet. has a small dipole, magnetic dipole moment, okay? So if I have a trap that is that doesn't depend on that it's state independent, like an optical trap. What's an optical trap? I get a laser beam, a powerful laser beam, and focus it on the atoms. So I get a powerful laser beam, like an infrared laser beam. I go with it through a lens. It does like this. No, anyone that did the optics course, this is the focus of the lens. And if you do all the calculations, atoms will accumulate here. Okay, this is a trap, a real trap. Of course, if I switch off, they fall. But since they are small magnets, I can apply a magnetic field gradient. So a magnetic field gradient pointing up, and this leads to a force because these are small magnets. So I can compensate gravity like this, and this is done routinely in labs. So when you need the cloud to expand for a very long time, you cannot allow it to fall because it will also fall a very long distance. Very long distance, a centimeter, okay? But if it's a centimeter, it's out of your imaging beam. Sometimes it will hit the wall of the vacuum chamber, so that's a problem. So if you have to let it expand, this is a solution. But the bubble trap is not like this. The bubble trap is not an optical potential. The bubble trap is what we call dressed state potential. Dressed states were first introduced by Claude Cohen-Tanucci. I think some of you know the book from quantum mechanics. You start with a magnetic trap. So I have a magnetic field that has, let's say, a harmonic profile. So this is what I'm plotting here is magnetic field versus position, okay? But if my atom is, let's say, spin down, it will see the magnetic field like a magnetic potential, like this. But if it's spin up, or the contrary, so it will see a potential like this, okay? So the magnetic field is only one way, but the potential that the atom sees can be a trapping potential or a anti-trapping potential. Up to here is fine, okay? Good. What are dressed states? In dressed potentials, we add to this problem radio frequency. So we connect the two like this. So the atom is, in the end, in a superposition of two spin states. Okay? When I do this in a dressed picture, it's like the potentials do like that. Okay? This is the magnetic field plus radio frequency. But you cannot have crossings, so you need to work out this in variational. I think it's a variational treatment, and then what you get is this. What you really get is this. You get one trapping potential that is like this, and another one that is like this. This is what the atoms see when they are in a superposition of two states, spin up and spin down, in the presence of a magnetic field and radio frequency. Okay. If I do things carefully, atoms will sit here. In one dimension, this is a double well. But in 3 dimensions, this is a shell. Do you see this? If instead of having X, I have R, this is a shell. So this is how you do a shell. The problem is the position of this minimum, it depends on the magnetic field and the RF frequency, radio frequency, the exact frequency. It's the balance between the two, because I have to really, it's this point where I do the transition. If I place an extra magnetic field gradient to compensate gravity, I mess up with my trap. So I cannot. So for bubbles, I cannot compensate gravity, okay? These two questions came yesterday repeatedly, so I think we should tell them. Okay, it's clear for everyone, I think. Good. So yesterday yes.
I was asking some people and I don't get it, and I didn't see it if you said it later, but where's the scale that we are talking about in the BCs, like nanoscopic?
It's tens to hundreds of microns in size, in trap.
Oh God.
It's huge for a quantum object. Okay. Yesterday we are manipulating the potential landscape. We were manipulating how can we trap the atoms, and everything is maybe too strong, but many things that we can do with that. But given one trapping landscape, like optical lattice or a double well or whatever you like, the whole dynamics is defined by the interactions between particles. You remember Gross-Pitaevsky equation? We have kinetic energy, we have the potential, and we have the interactions. And the interactions are really the main energy contribution. And the nice thing is we can manipulate interactions. So I want to go back to the blackboard once more to look a bit more careful on how can we manipulate interactions. I promise I will be short, so let's manipulate interactions. Yesterday, or I think the day before, I was talking to you about interactions, and I did this drawing here. I have an incoming wave. I have whatever I like, an interaction scattering center, and I have outgoing wave, and this outgoing wave is shifted compared to the original wave if there was no interaction. Okay, that was what we did. This was how we defined, or we came that we can substitute whatever potential we have here with an effective potential that is the billiard ball potential. So it's okay, good. But I want to take a closer look to the real potentials. The real interacting potentials, so between two atoms, as a function of the position, usually they have a general shape, and they are like this, no? So remember, we are in a center of mass reference frame, but for practical matters, you can imagine an atom coming in, comes in, reaches turning back point, and goes back. No, this is an elastic collision. Good. However, these atoms have internal an internal level structure. This is valid for, let's say, two atoms like this, whatever this is, spin up and spin up. But if this is spin up and spin down, or if it's a multi-electron system and I have some triplet state, or one triplet, one singlet, and so on, I can actually have many, many more of these potentials. Okay? And this is the key point here. We used to call this an open channel. Because the atom can come and go back, but there are, together with this, closed channels. So if the atom comes and changes state during the collision, it could get into a bound state of this closed channel. And never leave anymore. So it's like coming here and then suddenly be trapped. This is a trapped state, no? So it comes from potential that it has an elastic collision to a potential that has inelastic collision. Fine, okay, but you know what? This potential has several levels, and if one of these levels is coincident with the pair energy, this transference is more likely. So if I can control the spacing of the levels, so how they move compared to each other in energy, I can control the effective interaction potential. Do you follow me on that? Good. Nice thing is, these collisional levels are controlled just like Zeeman levels. So with an external magnetic field, you can control these things. So if I apply a homogeneous magnetic field that most of you have probably constructed in an electricity lab at some point, you can control the interaction. So in the end, if I have, there is again a lot of calculations, but I can write my interaction term. You know that G that goes into the Gross-Pitaevsky equation that looks like this. This becomes a function of the external magnetic field. And it's a function like this. There is a background value. There is this dependence. Okay? B is the magnetic field that you control externally, literally with a knob in the lab, because you're controlling current. This is the central magnetic field where the scattering length just go to infinity, and this is the width of this this feature. I'm showing examples, and this is called a Feshbach resonance. Okay, the name comes from nuclear physics, but it's the process resonance. So controlling the magnetic field, you can come to 0 in principle, okay, 0 depending on the background, but 0 interaction, very high positive, very high negative, And so you can change sign in an easy way, okay? So of course, since we are depending on how are these exact potentials, there might be atoms that have one of those, or several, or if they are too narrow and you cannot use for practical reasons, or they are very broad and good to work with, or they are at very high magnetic fields. You have a question? Yes. So for practical purpose, one has to look at it, but you can drive interactions with a simple magnetic field. Tell me, you have a question.
Thank you. That I thought that term, the A term in this expression, referred to sort of the interaction region. Is that a good way of sort of thinking about that A? And
Yeah.
if that's the case, I'm wondering what happens, or what's the physical implication of having that value be a positive quantity or a negative quantity based on how you choose the magnetic fields.
Yeah, okay. Thank you. Great. You can think of A as the radius of your billiard ball, okay? If it's too large, you start to have correlations between the particles, too large positive. First problem, so our mean field treatment breaks, first thing. Second thing, you start to have three-body recombination, because as I said, this is valid when I have a dilute gas with two-body, you have three-body, and then you just lose your system. There's a lot on this, but this is the problem for a very high positive. On the other hand, you can go very high negative, but I hope to show you today that if you go slightly negative, you also explode your BC. So, of course you can, but this doesn't mean it will be useful. I mean, you explode your condensate.
Yeah, thank
Okay.
you. Yeah, it just seems sort of counterintuitive to think about a negative.
But we come to that.
Thank
We
you.
come to that. Okay. These are examples of some Feshbach resonance profiles. This is for lithium-6. And this is interesting because this crosses zero with a very well-behaved slope. So you can make a non-interacting Bose gas with this. It's also very, very broad, you see? And it happens at a very high magnetic field. Another example, this is potassium. It's happening at around 224 Gauss. You see that this is around 800 Gauss, so it's this B0 that is very different. It's narrower also, but you can also work with that. Of course, since this depends on the electronic structure, I'm showing you lithium and potassium. And these guys are, these guys look like a hydrogen atom, so they have one free electron. So these are the most simple atoms we can have. But if I go to an atom with a very complex electronic structure, like, let's say, dysprosium, each feature of this, that the number of atoms is going down, is a Feshbach resonance. And this is going only to 70 Gauss. So there are very narrow ones, there are some large ones, and so on, but this is because of the electronic structure. I have one question from Batman, Bruce Wayne, maybe. Yes?
Thank you, Professor. My question is, what determines the width of this fresh bioresonance?
Electronic structure.
I mean,
It depends on these potentials. So it's how they interact.
but you have some kind of loss to have a finite transition, right? Right? Because if you don't have any kind of loss, you get the image from the
This,
top. Yes, they can go to infinite, right?
in principle, they
considering
can go
the-
to infinite, yeah.
But what kind of structure? I mean, physically, like spontaneous emission.
It's a bound state.
Okay.
They make a bound state, and they just leave as a molecule, as a droplet. Okay?
Okay.
It's bound states. Yes, so I think it's closer here.
Okay, my question is related with the magnetic field. What is
Yes.
the origin of this? It's Zeeman effect. It's what's the A factor is like it's related to the potential of the scattering. Okay, I think that you model this interaction including another term. You not the
You
Feshbach
model the
what's
scattering
the-
with other levels.
with levels.
Yes.
So you include
Just
the
like this.
spin orbit or
Just like this.
okay.
Just for the sake of example, okay, imagine that in this level is one atom like this, the other one like this. But you could have a channel that one is like this, one is like that.
Okay, so
So,
it's
and then it's
angular
a different potential.
Yeah.
So, and they behave differently if in the presence of a magnetic field. So, I'm not telling you, but this has been studied, and this has a chaotic behavior, whatever this means. Okay, good. Bottom line is we can control interactions, okay? And the important thing is that interactions, they define everything. We saw already. We saw that interactions define the shape of my density distribution. Interactions define the size of that parabola that I was drawing here. They define the healing length. But they define also, I've shown you this picture before, they define the speed of expansion of this matter wave. They define the size, but not only the size of the vortices. The vortices are there because there is superfluidity. If I don't have interactions, I don't have superfluidity. So the size of the vortices, the arrangement of them here are defined by interactions. This is a picture of a BC exploding. I'll come back to this. This is called a Bose-nova. When you go to negative interactions, it just explodes. So there is no ground state anymore on the Gross-Pitaevsky equation. And of course, for real systems, what they do, they yes.
Just about the vortices,
Yes.
you said some lectures ago that they carry a quantum of angular momentum. Is
Yes.
that right? Could we observe things like vortices joining,
Yes.
some of angular momentum?
You can make what's called giant vortices. Vortices with 2, 3, 5, 10 quanta of angular momentum, but they are not energetically stable. So you make them and they decay in single quantized vortices. Okay, but you can do it. We come back to this, and of course, this is the simulation of a soliton. Solitons are excitations, and they depend. The dynamics of this depends on the interaction. So everything on a BC depends on interactions. Okay, very good. I think that. So this. Yes, we have one more degree of freedom. that's maybe interesting for quantum computation. We have explored this, the external potential. We have touched the interaction, showing that we can manipulate those guys. But we have to remember that this is not a mathematical equation only. Psi0 represents a real atom. And as we told here, a real atom has internal states, spin states, angular momentum states. And in principle, I can take some of my atoms, all of them, half of them, and move them coherently from one state to the other and back. So I can manipulate this and have multiple BC components with each one of them with intra-particle interactions, but inter-BC interactions. So there is this term for state 1, this term for state 2, and there is the cross term of interaction. And I can bring one of them to the other state and back, so I can. This is a kind of a qubit, no? I think so, because it's a two-level system that I can operate. Actually, I can have more than 2 bits. Yesterday I learned that it's qubit, qtrit, 3-level, and qdit. Is that with many levels? So, Psi0 has an internal level structure, so one can play with that. Again, with the correct lasers, the correct frequencies for transitions between those levels. Okay, so this is another degree of freedom. Good. So, summarizing lecture 2, we can easily tune the parameters, and interactions are the most important energy contribution to the dynamics by far. Okay. So, lecture 3. Wednesday, yesterday, today we dive deeper with interactions, just because they are our most important ingredient on this soup. So, from yesterday, from a few minutes ago, interactions are the dominant energy contribution to the dynamics and to the static properties of a BC. So if I have to ask, if interactions are so important, why don't we add other interaction terms? If I have to choose, what interaction term would I choose? So the answer was here like 10 minutes ago, because I told you already that most of my atoms, most of the atoms are small magnets. So I can add to this equation dipole-dipole interactions, just like two magnets. And dipole-dipole interactions bring a completely new scenario to our problem. Okay, which are the possible candidates to study dipolar physics? That's what we call dipolar BEC, dipolar Bose-Einstein condensate. We can use neutral atoms with a large magnetic dipole moment. Why large? Because, you know, rubidium atoms, which are the most common atom, which is the most common atom for BECs, it is a small magnet. But it's so small that dipole-dipole interactions just don't play a role. It's too small. So I need an atom that has a large magnetic dipole moment such that this interaction is relevant in the dynamics of my problem. The other possibility is ultra-cold heteronuclear dimers with an electric dipole. And until 2 years ago, these guys were really a problem because they suffer from a strange problem named chemistry. If I make, it's true, it's true. If I have, I can make in the, we can make in the lab dimers. It's not really a molecule, but it's a bound state of, let's say, potassium and rubidium. So it's a dimer. It's a bound state, and this has a very, very large electric dipole moment. However, if it finds another one in the code cloud, it goes immediately in K2 plus RB2 and a lot of energy. It's chemistry. They just die out very quickly. This was solved after many, many years, like 2 years ago, not more than that. So now there are Bose-Einstein condensates of potassium rubidium dimers. This can change everything, but we're not into that today. Okay, this is very strong. As you know, any electrical interaction is much stronger than magnetic interaction. So, okay, good. So, in general, here I'm focusing on neutral atoms with a large magnetic dipole moment, but the physics is the same. I just need a dipole moment. Good. So before I go in, I want to look into the details of dipole-dipole interactions, because I want to show you why this is changing everything. So, dipole-dipole interactions. You might have solved this problem at some point in electromagnetism course. What's the energy of a dipole in the presence of a second dipole? No? If I have a dipole, like let's say D1, in the presence of a second dipole, D2, and they are a distance r apart, what's the interaction energy of those? I think all of us have, many maybe, worked this out at some point. And this potential looks like this. So, potential of dipole-dipole, okay? There is this term. This depends if they are electric or magnetic, okay? We'll come back to this soon. Then we have a 4 pi r to the cube, so, and then d1 dot d2 minus 3 d1 dot r d2 dot r over r2. Okay, this is the potential energy of this system. If we have electric dipoles, so if the dipoles are electric, like in KRB, this constant is just 1 over epsilon 0. And if it's magnetic, so for magnetic, I think you guess already, my gamma is mu0. So just the usual electric and magnetic constants in vacuum. Okay, good. Fine. So we have to work with this potential. However, in real experimental conditions, we usually simplify this because this is implying that the dipoles can have any orientation. So I have a, if you like, a magnetization or a polarization degree of freedom. I'm not doing that. I'm applying an external magnetic field. So all the dipoles, an external field, so all the dipoles are pointing in the same direction. So they are aligned. Okay? So this simplifies this equation. And when I simplify it, here, I get the following. So for aligned dipoles. So for aligned dipoles, I get this thing. VDD equals to gamma D, D square. I'm saying that D1 is equal to D2, so all the dipoles are the same. For pi, 1 minus 3 cos square of theta over r cube, where this theta is just the angle between the, it's this, sorry, it's the other one. It's the angle between the polarization direction and the line connecting the dipoles, okay? Nothing new to see. It's very straightforward to come from this to that. Good. Now I want to compare this interaction term. So remember, we are in the context of the Gross-Pitevsky equation. So I have trapping, I have kinetic energy, I have billiard ball interaction potential, and I want to add this. So I want to compare now the billiard ball potential with this. The billiard ball potential, first, is isotropic. It looks the same whatever the direction I have. This is not. This is anisotropic. It changes with the relative directions of the dipoles. So this means this potential, if I sum up, because in the end I will sum up over all anisotropic. I'll sum up over all particles. It will depend on the overall geometry of my system. So if I have a pancake like this, if I have a pancake and a plane and my dipoles are like this, crossing the plane, I have a dominant repulsive interaction. But if I have, let's say, a cigar and my dipoles are pointing like this, I have a dominant attractive interaction. It changes sign with the geometry of the system. It can be even effectively zero because at 57 degrees, something like this, you get a zero here. So if I have a collection of dipoles here, a collection of dipoles there, and I can move, then I can make it zero. Okay? So it's anisotropic first. That's a strong contrast with the short range, the billiard ball. But the billiard ball is also, as I told already, now short range. And this is not. This is long range. Why is short range? Remember, it carries a Dirac delta inside the billiard ball potential. The atoms only interact if they are on top of each other. This is not true for this potential. And what's behind that? What's behind that is that, so I come back one step. Why I have a delta function in my billiard ball potential? Because I got this, whatever, Lennard-Jones potential, and substituted by an effective potential that comes with this delta function, okay? All those calculations that lead to this transformation are not valid if you have a 1 over R3. Actually are not valid in general if you have an interaction potential. So let me write here. If the interaction potential is 1 over Rn, and n is less or equal than the dimensionality of my system, I cannot reduce this to a short-range potential, so to a Dirac delta potential. So Coulomb is also here. Now Coulomb is 1 over R. Anything else, 1 over R4, 1 over R5, 1 over R6, and whatever you like, you can reduce to a billiard ball potential. 1 over R3, you cannot. 2 and 0, you cannot reduce to a... So it's long range. It remains even if the particles are far apart. Okay? Good. But there is, I do like another argument why this is long range, and comes from thermodynamics. It's in the Landau and Lifshitz book of thermodynamics. And they show that while defining thermodynamic quantities, you assume that energy is an extensive property of your system. But for this to be true, interactions have to be short-range interactions. And the reason for that is that you always come across integrals that are interaction energy integrated in the volume, okay? If the interaction energy is 1 over R4, 1 over R5, and so on, these integrals converge. If it's 1 over R3 in 3 dimensions, they don't converge. So thermodynamics is not defined for, or thermodynamics, the way we study it, is not defined for long-range interactions, because the integrals don't converge. So you have to go other ways. So these two characteristics of this interaction change the whole game, because they are the opposite of the usual interatomic interaction that we are dealing with. So every single aspect of quantum gases is changed. So the ballistic expansion is changed. The size of my parabola is changed. The collective modes, the vortex structure, the thermodynamics, as I told you, is non-defined. Every single aspect is changed, just because interactions are the dominant term, okay? But there is more. Because I have a new and very different interaction term, there are theoretical predictions that show that we have many exclusive phenomena for dipolar system. They don't occur in systems that don't display dipole-dipole interactions. So there is like the Maxwell-Roton excitation spectrum. You can treat the extended Bose-Hubbard model because you have inter-site interactions. Whatever. This I mentioned, the chaotic behavior of Feshbach resonances in Fermi systems. Solitons, I told you yesterday or the day before that solitons in BECs, they only exist in 1D. They are only stable in 1D. When you have dipole-dipole interactions, they are stable in 2D. They are stable in 2 dimensions, mathematically. So you can explore liquid crystal models, and you can have some things like super solid-like states. Yes.
Just out of curiosity, the dipole orientations are random but fixed, or are they free to rotate?
They are not free to rotate. So we are aligning this then to a fixed direction by an external magnetic field.
Okay.
You can, so let me be, I think, more specific on this. When I'm treating here, I'm treating these dipoles all aligned in one direction. So there is an external field that aligns them, and this simplifies things a lot. But there are some experiments that allow them to be free. They are very beautiful and very difficult. I don't know the details, but I know that there is an experiment with chromium. Chromium is one guy like this, that the guy there in front says, I cannot change the position of the screwdriver because the magnetic environment changes and my experiment changes. It's like that. Yes. Sorry.
So my question is motivated by if your dipoles are free to rotate, the potential is 1/r⁴.
Yes.
So then they can become.
So they will become short range. Yes. Okay. But they will also. What I know from that is that they will form like textures, so domains of dipoles aligned. So it's a mess. Good. It's here. Thank you.
I think the question is very interesting because with K-move, you can see spin waves. You can create domains. You can skyrmions. Like skyrmions like a soliton in 2D. I think it's this interaction in playing the situation. You'll be many interesting things in spin waves and spin dynamics, I think.
Good, thank you. Okay, I think this is the last time I come to the blackboard, but I'll show you a few examples on how the physics is changed with dipole-dipole interactions. But before, I want to, there will be a parameter that will appear everywhere, so I think we should define it so you know what we're talking about. I rewrite this for magnetic dipoles. So here. So for magnetic dipoles, I write like this. So dipole-dipole is 0 mu square over 4 pi 1 minus 3 cos square theta over r cube. Okay, we can define a characteristic length. It's just it's just a parameter right now. Okay, characteristic length. That's called ADD, just like you have A for dipole-dipoles, and this is written like this. m mu square over 12 pi. There is a reason for these prefactors, h bar square, okay? So you define this characteristic length just to compare with the scattering length. And what really appears in dipole-dipole experiments is this quantity, is this epsilon dd, which is the ratio between the characteristic length of the dipole-dipole interaction and the scattering length. In the end, we are comparing how much energy I have in the dipole-dipole interaction, how much energy I have in the short-range interaction. It's a way to quantify the competition between the interaction terms. And then when I write this, this is this. So this square, this scales with the square of the magnetic moment, the mass, and the inverse of the scattering length. So you see, we started today showing that we can manipulate scattering length. So we can manipulate how much the dipole-dipole interaction, how much this is playing a role. If I have a very large scattering length, this is close to 0, I don't care. I don't care about dipole-dipole interactions. If this is small, I have the dipole-dipole interaction playing a role, okay? This is defined like this because dipolar Bose-Einstein condensate in a spherical shell, it's just how we define it. In these conditions, if EDD is larger than 1, the condensate is unstable. It just explodes, unstable. And if it's smaller than 1, it's stable. Okay, this is how people decided to define this thing. But of course, if I go to other traps that are not completely round, this is not true anymore. Okay, good, fine. So let's see candidates. Yes, this is what we did again last time in the blackboard. So let me show you a table just to illustrate this. I have rubidium here. Magnetic moment of rubidium is 1. Then I have mass. I have typical scattering length. This is this A0 that appeared, okay, before manipulation. So this dipolar strength, the EDD, is nothing, 0.07, means nothing. Rubidium doesn't show dipolar effects. The first atom that has shown dipolar effects was chromium. Chromium is the atom with the largest dipolar moment in the periodic table, due only to spin. That's important. It's 6, and then the dipolar strength is 0.16. You have measurable effects. And then 10 years ago, we got 2 lanthanides in the BC regime, erbium and dysprosium is huge. Dysprosium is the largest magnetic moment in the ground state of the whole periodic table. So it's the most magnetic atom you can have. This is due to spin plus orbital magnetic moment. Good. So dysprosium is like this. That's why. So dysprosium has this. In the end, everything boils down to electronic structure. But dysprosium has this electronic structure. So the ground state looks like this. And this is how you distribute the last electrons on these 4f10, 5s2 levels. Dysprosium is here as a lanthanide. We never look to that, so these are the lines we forget from the periodic table. When you equate the orbital magnetic moment is 6, the spin magnetic moment is 4, and the total magnetic moment is 10. And it's the largest you can have. Of course, once electric dimers are now available, the electric dipole moments are much, much larger than that. So nice things about dysprosium, it has this complex electronic and collisional properties. It has abundant bosons and fermions, so one can look into the two directions. So here we only touched bosons, but it has fermions also. There is this low field Feshbach resonances. There is a full line of study of variational of fundamental constants using dysprosium. I'm not touching this here. And of course, laser cooling is possible. Okay, how dipole-dipole interactions modify the properties of the BC? I have a few examples here to try to convince you that these really are modifications. They are important in modifying these systems. Let's look at it. Magnetostriction. Yes, example one magnetostriction. This is, you see, this is aspect ratio. So this is expanding cloud, okay? So this is time, it's expanding. And I'm measuring the ratio between one direction and the other direction. You saw this picture before with me. It changes, no? The dashed line is what you expect for a non-dipolar BC. The blue line is what you get for a dipolar BC with the field in one direction, with the magnetic field in one direction, and the red line is what you get for the magnetic field in the other direction. So you change the speed of expansion, but you change also the ground state. These are pictures of dipolar BC. This is erbium, with the field pointing out of the screen, and with the field pointing to the top, and the cloud elongates along the magnetic field. So this is a round trap. This is a sphere. And still the density distribution doesn't match anymore the potential. It elongates, okay, along the field. So it's changing static properties. But it's changing also the excitation spectrum. This is how you calculate it. I'm not going into that, but you see the epsilon dd appearing here. So if it's 0, of course you get the regular excitation spectrum of a BEC. And this is how it changes. You see, this is the behavior of a low epsilon dd, so close to 0 excitation spectrum. This is energy, and this is essentially momentum. And this is how it looks like when you have a large epsilon dd, a large magnetic interactions. It changes quite a lot. Instead of being almost monotonic going up, it has a dip at some point. So it changes the behavior. Also collective modes, this you see, this is a BC, and we let it oscillate, okay? We give it a kick and let it oscillate. And these are oscillation frequencies with the field in one direction is the black line, and on the other direction is the red line. It oscillates differently. It's just due to this contribution. Okay, that's not all. This is an example I like a lot. Maybe because I worked with this, but the stability diagram and the collapse of a BC. Essentially, the stability diagram is where in the parameter space a BC exists. I told here a few minutes ago that for negative interactions, it explodes. It doesn't exist anymore. So this is the stability diagram is a map of where it's stable, where it's unstable. And the collapse is what happens if I move quickly from the stable to the unstable region, so how it explodes. So non-dipolar BC is very boring, actually, because it's, so this is critical scattering length. It's stable for positive, it's unstable for negative scattering length. Energy is so dominant, interaction energy is so dominant in this system that as soon as you cross to an attractive, effective, attractive interaction potential, these guys, the Gross-Pitaevsky equation has no solution. Okay. Actually, it's not 100% true that this is zero. It depends a bit on the trap and the number of atoms. But if you plug typical numbers, it's like this. So you can be negative, but you can be almost nothing negative. So for all practical reasons, if you cross from repulsive to attractive interactions, this thing explodes. Okay, good. When you have dipole-dipole interactions, things are different. So the red line shows the critical scattering length as a function of the trap shape. So if I have a Seeger trap shape, which is this side, so and the dipole-dipole interaction is attractive, so it's negative. It's a negative energy contribution. I must have a positive scattering length to compensate it, or it will explode. On the other hand, if I'm on this end and I have a dipole-dipole interaction that is mainly positive, so repulsive, I'm allowed to have very large negative scattering lengths, very large negative attractive, so attractive contact interactions. So this changes a lot in comparison to this boring flat line on zero. So this is changing. Actually, we've been looking on how to probe this region at some point. And we had a BC like this. And then we sliced it. When we slice it with an optical lattice, no, I'm playing with the external potential. Each one of those is, so this is what we have here. But this, each one of those is what we have, there. So with the depth of my lattice, I can explore this region. This is what we did. And it's funny because, you see, we measured very negative scattering length, very attractive short-range interactions to show that the dipole-dipole is changing where my BC exists. It exists above this line and it doesn't below this line, okay? And of course, with no dipolar interaction, it's just this boring flat line on zero. Good. Fine, everyone? But there is more. This is a beautiful experiment because, you know what? I cannot do this experiment, but I can simulate. Since those simulations, those lines are simulations with different number of atoms, they match so well experimental data, I can allow me to simulate this. What's the difference between this and this? I will see the contribution of long range at the long range part. Because here, I don't have my neighbor to have a long range interaction. Here, I should have long range interactions. And the long range here, they are attractive, so they have a negative contribution to the energy. When I do the simulation, I see that this is the line of this, but if I had no neighbors, I would be even more negative because I don't have the long range part of the interaction. So I do see anisotropy and long range on this kind of system. To finish, I want to see the collapse BC. This is, so if I jump from the stable to the unstable region, I got exploding BC. It just expels atoms out of the BC because they don't fit anymore in the ground state. This is what is called Bose nova. So this is time moving, so from A, B, C, D. So you see that it's going down because it's expelling atoms. And this explosion is isotropic, as you expect, because the interactions are isotropic. That's not the case for a dipole RBC. This experiment, the top line is experiment, the bottom line is simulation of the Gross-Pitayevsky equation. It explodes in a very beautiful and different shape. But if I change my trap, because if I change the trap, I change the contribution of the dipole-dipole interaction, meaning that the explosion is also different. But still, simulations match very well the experiment. So I hope I have convinced you that dipolar interactions are this rich new ingredient to the Gross-Pitayevsky equation. No? That has this anisotropic and long-range tail, and we can modify every single aspect of quantum gases. And of course, that there are new phenomena. For what I planned, I have one last topic that I'm not going into. I just touch it so we can have a proper ending on this. We can go beyond. We can go beyond mean field approximation. You know, everything we did, experiments and simulations, was mean field. But that's not true. I told you, Gross-Pitayevsky equation is modeling 99-point-something% of the experiments. But we still have that 1%, that few percent experiments that are not modeled. Where are they? I come back to the first day, because I wrote on the blackboard, I wrote this, A naught, and the sum of everything else. I think was something like this. No? And we say, oh, we disregard this thing. Okay, they come from this thing, which are quantum fluctuations. They are measurable. And this is, so this is what I'm not showing you. So we have mean field, but we can have beyond mean field effects. I'm just showing you the, sorry, where is it? Here. The beyond mean field effect, that is this term here, Li-Huang-Yang term, for dipole-dipole interactions, is scales like this. So here is S-wave scattering length. Here is the strength of the dipole-dipole interaction. And when they enter the Gross-Pitayevsky equation, which is written up there, it multiplies density to the third power. So if density is low, this is just not relevant. When I go to very high densities, this starts to be relevant, okay? And unfortunately, I won't be able to show to you, but this gives rise to a very hot topic in dipolar quantum gases today. That is, you can see supersolids. You can see a super solid state. Maybe you allow me 5 minutes. Yes, good. When I have this, this term in there, the condensate, it breaks in islands. Okay, it just breaks spontaneously. Okay. these islands, they don't expand. Here you see, this is a condensate, a regular condensate. I let it go, it expands. These islands, they almost don't expand after a very long time of expansion. This is a droplet. Like a water droplet, if I let the gas go, it will expand. If I let the droplet go, it don't. It keeps its shape. It's the same. This is what is called a quantum droplet. Okay? So at very specific conditions, this happens here. You see, this happens in a very narrow range of scattering lengths. Okay? Don't worry. Just follow me for the physics. But if I let those droplets still expand and recombine, what we get if I recombine several wave functions? Interference. Fine, I get interference. So I want you to look to this. You see gray lines here. These are single shot interferences. So you see interference, but when you average over many of them, the interference smears out. You don't have interference if you average, which means in every realization, the phase between those islands is evolving randomly. Okay? Because then when we average, the random character just kills the interaction. But in a very narrow range, you see, going from 89A0 to 92.5A0 on the scattering length. This is a very tiny range, which is a very tiny change in the magnetic field. I average many, and I still keep my interference peaks. This means that the individual islands that I created spontaneously, they have the same phase. Do you follow me on that? So when a quantum system, a quantum fluid, one spontaneously break in parts, which looks like a solid. No, a solid is matter, no matter, matter, no matter. And these parts are still superfluid, so they have the same phase. This is a supersolid. And this is very hot right now in the field. Okay, good. So last. So mean field theory. So quantum gases are cool, I think. I think you agree with me with that. Mean field theory accounts for almost every single experiment. We can go beyond mean field to account for what's left. And this is a really exciting and still developing field. To end, we do some of this, not everything, but some of this in São Carlos. In quantum gases, we have Professor Vanderlei Banhato, myself, and Professor Patrícia Castilho. In cold atoms, in general, we have still Philippe Courtet, Luis Marcassa, Raul Celestrino, and some other researchers that have been doing a very beautiful job on this field. So if you have the chance at some point, come see us, come see the labs, come see what we do. There will be nice things to see, okay? So with that, I leave my contact if you like, and I thank you for your attention. Are there questions? If not, as usual, I'm here today until lunchtime. Good, so I think coffee break time? Good, coffee break, thank you.